Good morning, everybody. It's morning. It's 5 o'clock in the morning, 5:10. And today we're going to continue to try to understand quadratic equations without using that word and without introducing any kind of formulas that you have to remember. Okay? And we want to do this again the intuitive way. Let me use a different word. All you need today in order to solve quadratic equations is a pencil. You need a straight edge, okay? And then you need something circular. Now, ideally you'd have a compass, but I don't have one with me at the moment. It's sitting in my desk at school, and I'm at home, so I have the lid of a Skippy creamy peanut butter spread peanut butter cup, okay? Peanut butter jar. So here's what you do, okay? So this is the big, difficult mathematical concept of solving a quadratic. Now, this method does not require the use of a calculator. It doesn't require the memorization of any weird formulas, and it was invented a long time ago in the 1600s by the same guy who came up with the coordinate plane, René Descartes. And I'm going to write his name up there in a second because this is so ingenious. This way of doing this is just unbelievable. That I don't know why we don't teach this. So, like we've said before, if I have been teaching quadratics now for 5 years, and every year I ask my students at every interval, at the end of every class, what is a quadratic? And they don't know. Okay? They don't know. Even after teaching the whole section, they don't know. And you know what that tells me? It tells me I didn't teach them what a quadratic was, right? And if I ask you what a chair is, you're going to point to a chair and say, that's a chair right there. And then if I ask you to describe a chair, you'd tell me, well, it's something you sit in. You would just go all into all these details about chairs. Maybe you could even go to carpentry class and learn to build one, okay? Chairs are easy, okay? But when we start talking about math, people start freaking out because we throw a bunch of numbers at you, formulas, theorems, right? What if we didn't need any of that? What if all we needed was a Skippy peanut butter lid? Okay, I like this. This is how math should be taught. IMHO. There's nothing. Look, hey, no, this is not a disparagement of anyone because the only time I've ever been able to teach quadratics this way is in geometry. Within algebra, usually we use algebra. Okay, so when if I say this is the way it should be taught, I don't mean that if some other teacher taught it a different way, that teacher's wrong, because I am that teacher, right? I'm teaching it a different way too, right? I'll teach it the way where we show the quadratic equation, or we learn the vertex form and we learn to factor and all blah 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 blah. But I know from my personal experience in the class, and you know from your personal experience in the class, that you can go through that and you can learn that formula and know absolutely nothing. No, okay, gnosis, right? Gnosis, this Greek word, knowledge, okay? Do you know? Can you really tell me what is going on? And usually the answer is no. Okay, so just draw a circle, okay? So take whatever you've got and draw a circle. You need a pencil for this. So the René Descartes said the only thing you need, actually I think I'm quoting Thomas Carlyle here, but it's the same. Descartes and Carlyle, both geniuses from the 17th century, 1600s. the big names are Gauss, Euler, Descartes, Carlisle. Just draw a circle, please. And you have a circle. And now, Mike, this is that like to the math administrator or whomever is watching this. Have I done anything wrong yet? No. And to my students, have I blown anyone's mind yet? We drew a circle on a piece of paper. It's not that big of a deal. Okay. So now what? Okay. Well, now we're going to draw in our diameter, right? I'm going to draw a diameter. And we're going to draw this diameter at like, let me use a protractor to kind of show you what I'm looking for here. I want to draw the diameter like, think about this. So this is why I bought you these compasses. See how I've got the bottom line there, just touching the bottom of the circle there. And then I'm just going to put a little dot right here. Okay, that's what that little hole is for, by the way. Okay, so you can do this kind of thing. And then basically you want to draw a diameter that goes through the center of the circle and kind of hits right about there. Okay, so we're just drawing, and we can construct a circle where we get its perfect diameter. Like the diameter is the right at there, so I'm trying to estimate it visually, right? So I kind of want to draw a diameter. Maybe I need to move my point a little bit. Let's find the diameter of the circle. This is just a drawing. Yeah, I'm going to have to move my point a little bit. But not too much. Okay. Because, the diameter can be any point around the center of the circle, right? All of these are diameters, right? So can I sort of visually identify the center of this circle? Just do it freehand, like where's the center? Right there. Okay. Ish. Center-ish. So now the diameter is just a straight line that passes through there. Like that. I was a little off. It's okay. Remember, my diameter can be any. I think I can make it work with my point. Okay, so look what you can do. So you see that? That's the point of this line. That's why I bought you this very special compass. Not all the compasses have these things on them. You see how I do this now? So now I've got my center, which we've estimated visually, and I've got this point down here, right? Let me make sure you can see all this. See that dot right there, and that dot right there, and that dot right there? I want you to draw a line a dotted line. So let me show you what I'm talking about. So I need you to draw a dotted line starting from the inside of the circle, going through the center. Okay, so skip this part. This was just for measurement. This has nothing. Okay, starting here, just draw a dotted line. Just draw it light, right? Light dotted line going through the center. And we'll fix this. We'll make it look pretty here in a minute. Okay, and all the way down to this point here. Okay. Alrighty. So now let's give it a little bit more character. So now we back off. This is more artistic. You know, in geometry, I always tell my students, if you're not using a compass and a protractor and a pencil and drawing, you're not doing geometry. And in math, in general, if you're not writing, you're not doing math. So we're writing. I mean, we're using a pencil. And I'm just sort of filling this in. And I really think taking your time with this is super important. Make it pretty. Be artistic. Take that person sitting in the classroom who thinks they're bad at math, but they can draw really well. Okay, guess what? You're about to shine. Okay, so now what have we got? Okay, we've drawn a line. Now, have I blown anyone away yet? I've drawn a line. Okay, we know this is the diameter of the circle, and then there's this thing sticking out, going to the bottom. And that point, if you forgot, now wait, how did he get that point? That point is flush with the bottom of the circle. Okay, that's where I got this point. And what I want you to do now is take your ruler. Okay, it doesn't even have to be a compass anymore, it's irrelevant. Just take your straight edge or whatever, and so what we need now is we need to be perpendicular to this point. Maybe we do need the compass. So we need to be perpendicular to that center point. Now, how would you do that? Okay. Show you. So there's 90 degrees, right? Make a little mark. Again, a compass is what we really need, but we don't have one, so we're using what we have. And this is so cool when you see it. So here's another, just flip the compass upside down and 90 degrees. Okay. So I can be fairly certain that if I draw, so let me just make it just a quick guideline. So this happens a lot in geometry where you're making these little guidelines that you don't actually use. So you want to draw this very faintly because it's not actually part of anything. It's so faint you might not even be able to see it. Let me see if you can see it. You can kind of see that, right? The faintest possible line imaginable. Yes? Just to guide you. And now, from this point here to this point here, we're going to draw a line. Okay. Anybody? Have I lost? There's nobody's lost yet, right? We've drawn some lines. Now, let's notice something. There's a shape here that you should be noticing. What kind of shape is this? This is a triangle, but it's a particular type of triangle. What type of triangle is it? What angle do you think is right here? It's 90 degrees, right? I mean, I literally did a 90-degree perpendicular. So we can go ahead and darken this in because this is going to become the important part of our drawing. So I'm going to just darken that in a little bit. And I'm going to commit this line here from the center of the circle down to the bottom right there. Okay? And what do we call the distance from the center of a circle to the edge of a circle? It's a radius, right? So that's the radius of the circle. There's another radius. Here's another radius. Okay? So these are important. This is important. This distance right here is a radius. That's equal to the distance from here to here. And that's equal from the distance from here to here. This is all important. All right? Radius. Very important. Huh? What do you call this line from here to here? The hypotenuse. Yeah? This is the base. This is the height of the circle. We could find the area of the triangle. We could find the area of the triangle. Base times height divided by 2. Yeah? We could find this, right? This is a squared plus b squared equals c squared. So c equals the square root of a squared plus b squared. It's very simple. Yeah? Okay. Now, we're going to label these points. So we're going to label this point right here point Q2. Okay. And this point right here is what we're going to call the origin, or O. This is not 0, this is an O. Okay. Okay. And then right here, put a dot right here. And this is point Q1. Remember, the distance from Q2 to O is the same as the distance from O to Q1. This is the center of the circle, so these are radii. They're equal to one another. All radii are equal to one another. Now, this point down here, we're going to call A. And this point right here, we're going to call P. Okay? Alrighty, so I'm going to let you get that drawn. Okay, now here comes the genius of René Descartes. And at this point, I feel like writing his name. René Descartes. So this is René is a guy. René, R-E-N-E. And above the E, we put a little accent mark because that's how his name is spelled. And then Descartes looks like Descartes. Okay? So Descartes is D-E-S. C-A-R. And then T-E-S. Descartes. Okay? So René Descartes was French, and in French, you put the accent here over this E, and then you don't pronounce the S's. So it's just Descartes. Now, you might recognize something. If you say just cart, and then you add Asian, you have the Cartesian plane. And that's just the XY coordinate plane, right? That coordinate plane right there is the Cartesian plane. This dude invented it, right? It's the 17th century. So this was a 17th century philosopher. And back then, philosophy, it wasn't just restricted to, like, you know, what is the difference between good and evil and all that. It was everything. It was all of science and math was called natural philosophy, and so this was the 17th century. And remember that for centuries you -1 for the actual years. So the 17th century was like the 1600s, okay? Okay, so this is his method. Now, I want to show you now what Descartes figured out. So this is just brilliant. It's absolutely brilliant. So what he figured out was, if you have an equation like this, x squared, this is a general form, equals 2 times the radius of the circle. So the radius is r. 2 times the radius, x, and then plus or minus s, where s is some perfect square. Okay, I should write that down. You know, r is the radius, and s is a perfect square. Okay, I need to drop this down, and then drop this down, okay? And then cap off our, yes? Okay, is everybody cool? So now we can make these up, right? So I'll give you an example. Here's an example. So this is Descartes' little formula, okay, or form. So this is Descartes' form. notice that accent mark actually comes after his S because his name includes the S. Descartes' form. I'm not going to call it a formula. It's not a formula. It's just a form. Is this okay? So let's look at an example. Okay, so here's an example. Here's an example. What if we had this equation? You ready? X squared equals 3x plus 4. Okay. Now, how does this correspond up here? Well, it says that the thing before the x is 2 times the radius, and we've written a 3 here. So we should go off here and say, well, you know, the number right before the x is twice the radius. Wait a minute, what's twice the radius? It's just a diameter, right? Twice the radius. So let's put a little semicolon. So in our case, we have twice the radius, or 2r, equals 3. Okay. So what's the radius? 3 over 2, 1.5, right? So the radius is 1.5. That's that distance here. That's that distance here. The whole diameter of the circle is 3. Now, I hope you're starting to notice some real foundational relationships here between what we're doing and like everything we've done before. Now, so get that written down, and I want you to try to internalize everything I just said. All right, think about the geometry. Forget about algebra. Just forget about it. Don't think about quadratics. Just write this down, and then look at this and look at this, and the 2r and the 3, and then look back here. Remember the r is the radius. Okay, 4 is a perfect square, right? 2 times 2 is 4. That's important. So this is 3. This radius is equal to this radius. This, if 2r equals 3, then r equals 3 over 2. 3 divided by 2 is 1.5. Okay? Half the diameter. Okay, so twice the radius is the diameter, so the diameter divided by 2 would be the radius. And we're all cool on that, right? Okay, so just look at that for a minute. Okay, so now the other thing to recognize here is that S is 4. Okay, S is 4. So over here in our notes area, we should put another note. We should write S equals 4. Now here's the amazing thing about this, okay? This is so cool. So this distance from P all the way to Q2, this line right here, the whole line, that distance, if you can find that distance, like that physical distance, the geometric distance between those 2 points, is the positive, it's one of the answers, okay? It's one of the solutions, it's one of the roots of this quadratic equation, okay? That's just absolutely It's just absolutely fascinating that's true. That if you can find the distance from Q2 down here to P, you have found this distance is one of the answers to the quadratic, like the solutions. So we need to do a couple things here, right? We need to identify a new letter in order to continue, and that letter is B. So I want you to do that so over here in your notes. So let B, to put this in notes, let B, so we're like defining something, let lowercase letter b equal the positive square root of s. Okay, so everybody's sticking with me here, right? S is 4. So we can say, we can use our cool math thing, therefore. Okay, and don't worry, I understand some people watching this may not know what this means. This means therefore. We just don't want to have to write out therefore over and over again, so we use this little triangular series of dots. Therefore, if we apply it to our problem, where s is 4, therefore, in our problem, b equals the square root of 4. Just the positive square root, okay? Well, what's the square root of 4? See, it's like leaving no one behind, right? Like the Rangers. If you're a Ranger in the Army Rangers, you never leave a man behind, okay? Or a person, never leave anyone behind. And if I'm extending this metaphor as your teacher, if we're all Rangers, I don't want to leave you behind. The square root of 4 is 2. So b equals 2. If b is the square root of 4, then b is 2. End of story, right? Okay. Okay. So let's keep going. So I need to point something out here. So if 2 is the square root of 4 and b is the square root of 4, then b squared is 2 squared. Okay? Do you get that? So over here we can just put another little parenthetical. B squared is equal to, if b is 2 and we want b squared, then b squared is just 2 squared. Okay. This is nobody's blown away just yet, right? Okay. So now we're going to write down like the answer to the big question, which was how do I get both of my answers now? You've shown me that the distance from Q2 to P, that's one of them, but I don't know how to find that, right? Because we don't, you could find it, but you don't know this distance, so you kind of lost, right? You know the height, but you don't know the base, because you don't really know this distance here. You can't quite find the hypotenuse yet, so you're kind of like, well, so far I'm getting a lot of useless nonsense here. So this was Descartes' solution. So let's write this down. So here's Descartes' general solution. This is the general, pardon me, the general solution. We're going to stick the numbers in a second. But the general solution is the roots. Okay, what roots is another way of saying the answers to this question, to this quadratic, the solutions, the roots. In other words, where this crosses the x-axis, the roots of this equation which we wrote up here, the roots of x squared equals 2rx plus s. So right now we're just considering the positive case here because we had a plus 4, plus s may be found by solving this, okay, are equal to Rx plus b squared. This is worth just staring at for a minute. I mean, this is big. This is big stuff. So the roots of our equation are equal to 2 times the radius x plus the square root of this term squared. Okay, so 2 squared. So let's start plugging some numbers in, right? In our situation, so let's apply now. So let's apply this to our example. Okay, let's apply it to our example. So what's our example? X squared equals 3x plus 4. Okay. So I'm going to keep that lined up with this. So our example was x squared equals 3x plus 4. It says here okay, just trying to make sure that you can see what I'm writing. Yeah. It says here, look, it says here that the roots or the solutions, this word root means the answer, the solution to the quadratic where it crosses the x-axis. If you were looking at a picture of the quadratic, the roots would be equal to 2 times the radius of this circle, aka the diameter, plus b squared, or x plus b squared, okay? So let's remember a couple things. R is the radius and S is a perfect square. So the number in front of the x is twice the radius, so the number 2r equals 3. So this 2r is 3, S is 4. We already went over that. All right. So now we can find out the coordinates of this point P. With O as the origin. Okay, so now we're going to find the coordinates of point P. So this is just, I'm just blown away by this. All right, so this point P here has the coordinates of, and this is just dramatic, of B. So I'm going to write this up here, B, comma, so B is the x value. We already found B. The y value is negative r. So the negative of the radius. So B, comma, negative r. So what? Let's think about what we know. We already know what r is. We already know what B is. All right. So we said that the diameter, 2 times the radius, was 3. So what's half 3? 1.5. So the coordinates at point P are 1.5, or hang on, so that's the y value. I'll get to that in a second. So B is equal to 2. See, B was the square root of this number S, so B is equal to 2. So the x value is 2. You can think about a coordinate plane now and think where that would be. And then negative r. Well, that would be negative 1.5 or negative 3 over 2. If I want to find r, okay, I'll just show it to you over here, okay? So you need r. Look, let me do it over here. Let me do it right here, okay? On this one. So this is the radius, right? This is what we call the radius. And the radius is always, we always use the letter r. Okay? So what's our radius? Well, we were given that 2r equals 3. So the diameter is twice the radius. Okay? So in our example, if 2r, or the diameter, right? If the diameter is 3, then the radius r is, right? And we'll show the math. So here's the math. 2r equals 3. We divide both sides by 2. Cancel, cancel. And you get the radius by itself equal to 3 over 2. Okay? Or 1.5. And so we can put 2 comma negative 1.5 or 2 comma negative 3 over 2. So we'll just put negative 1.5, and if we need to, if it's going to be helpful, we'll put in negative 3 over 2 if we need to. I'll just put in negative 1.5 so you can actually visualize it. So that point right there on a coordinate plane would be in quadrant 4, you know, because the x value is positive, the y value is negative. The only place that's true is in quadrant 4. So that must mean that A has the same y value, because A is on the same horizontal. So we don't yet know the x value of A, but we know the y value of A is also negative 1.5. Okay, starting to fill in some details here. Okay, now what else do we know? Can we find the distance from O to P at this point? Do you think we can find the distance from O to P? Can anyone think of a way to do it? Just think about a triangle is all I'm asking. I'm giving some time. So I'll now tell you that you got to think about radius. Okay, you got to think about B. Okay, what is B? B is telling you the distance from A to P. That's what it's telling you. So that means that the base of the triangle, okay, write this in, base is equal to 2, okay, which is base is B, right? It's not that complicated there, okay? So the base is 2. What's the height? Remember that this is a radius, this is a radius, this is a radius. The height is the radius. We already found the height. It's 1.5, right? So the height, let me take my paper here and turn it sideways so I can write it like this. The height is 1.5. HEIGHT. Okay. It's the height. So again, now I ask you, now you've got all the information in the world. And we should add something. We should remind ourselves that this height, this is the radius. Okay? So I think I told you this at the beginning, and certainly my old students know it's all circles, man. All of math is just a bunch of circles. So like the whole system of mathematics can be done. The Greeks did it. The Babylonians did it with squares. Okay? The Greeks did it with circles. And now we punch this stuff into calculators and have no clue what we're doing, right? So can we find, just forget about all this for a second, can we find this distance now? Using the Pythagorean Theorem? Yeah, of course we can. So we can write something like distance from O, not the sign of 0, that's an O, to P, well, how will we figure that out? So it's just remind ourselves that, little reminder, remember a squared plus b squared equals c squared. Right, and that's the Pythagorean theorem. And you all know that if I take the square root of c squared and I take the square root of a squared plus b squared, I can find c. So let's use our big therefore fancy mathematician symbol. Therefore, c is equal to, because it's geometry, we only care about, there's no such thing as a negative distance in geometry. It's just the square root of a squared plus b squared. Okay. Like that. Just remember that. You already knew that. I haven't told you, I've literally told you nothing today that you didn't already know. Okay? Except this. Yeah, this is the, and this. This is a fantastic solution. So let's apply the Pythagorean theorem in our situation. What is our A? Well, it doesn't really matter. We can make this doesn't matter, right? These two don't matter because they're addition. So this can be A can be 1.5 and B can be 2. So what you end up with is, we'll say something like let A be BE, right? Be the distance AO, okay, which is just 1.5. That's the radius, okay? And let BE let B be the distance from A to P, which was, this was the amazing thing. This distance from A to P is the square root of 2. Okay, so when you're given this quadratic equation like this, this is the let B be distance AP, which we already know is 2. The distance, the base of the triangle is 2. So let B be AP, which is 2. Okay. And I'm going to put that as a base of the triangle. Okay. Okay, stay focused, folks. All right, so let's move this up a little bit. Can I zoom this thing in? Will it really help? Yeah. Okay. So let's plug it in and figure it out. So the distance OP is C. Right, in our thing. Therefore, the distance from O to P, okay, this segment here, is equal to the square root. Now this is where that is going to come in handy, knowing that 1.5 is 3 over 2. Okay, that's going to come in handy here. Is equal to 1.5 squared. So write it was 1.5 as 3 over 2, and your life will be easier. So that's 3 over 2 squared. I'll show you why in a second. Why was this the better choice for this thing? It's all got to do with square roots and squares. Plus b squared. And what was b squared again? What was b? B was 2. Okay, plus b squared plus 2 squared. But before I write that, I want to ask a question. Okay, so where do I want to ask this question? I guess I'll ask it down here since this is where you're writing. Okay, so just think about this. Like, if b is 2, then b squared is 2 squared. But can I write, is there any way I can write 2 as a number with 2 in the denominator? Sure. Like, so, 2 is just equal to 2 over 1. So if I want to make the bottom number be a 2, I just multiply by 2 over 2. And I get 4 over 2. So another way of writing 2 squared would be, so just to say therefore, right, b squared is equal to 4 over 2 the whole thing squared. Like that. So let's use that one. So let's put it over here. Plus 4 over 2 squared. Okay. All right, get that written down and think about it for a second. So there was actually a reason for doing this. Okay. So now, when we square a fraction, okay, here I want to point something out. When we square a fraction, we square the top number and the bottom number. Okay, so we square the top number and the bottom number. So you can't add these together. Okay, it doesn't, not because of the parentheses. You can't do addition before parentheses. That's order of operations. So first we need to square these numbers out, and then we can add them. So let's keep going. Trust me, the end of this road is worth the walk along the road. Okay. Just trust me, please. Okay? All right. Okay, so you can do this in your head. What's 3 times 3? That's 9. Okay, so this is 9 over 2 times 2, 4, 9/4. Now you're going to see why I made you turn this in like this. Now what's 4 squared? 16 plus 16/4. Now can we add, now is there any parentheses? No. So can we add these together? What does this equal? Remember, you add the numerators. 9 plus 16 is 25. So this is equal to the square root of 25 over 4. Now you might think, well, darn, I still don't know anything. But did you know that you can, whenever you're multiplying or dividing, you can split up the square roots how you like? So this is actually the same thing as saying the square root of 25, which you know off the top of your head, divided by, see how I've been able to just split the square root, but divided by the square root of 4. Do you know the square root of 25? Absolutely. So that would be 5. And now what's the square root of 4? 2. 5 over 2. So that's actually OP. Okay, distance OP, distance OP. Now it equals 5 over 2. Now how far, what is that distance? What is this? 2 goes into 5 2 times, with 1 as a remainder. So it's 2.5, right? 2.5? Is that, you see 2 goes into 5 2 times? And then what's the remainder? 5 minus 4 is 1. So it's 2.5. Right? And then to get this into an improper fraction, it would be 2 times 2 is 4 plus 1 is 5. So you see that's the improper fraction. This is the mixed fraction. What's the decimal? 2.5 is 2.5. 1 divided by 2 is 0.5, so it's 2.5. So now we can get back to using kind of like up here. We're going to get back to our triangle now. Up here, we use the distance, like we want a number, right? The decimal distance. So we know that this distance is 2. This distance is 1.5. So now we just found this distance here. This distance is 2.5. Okay. That distance right there is 2.5. Right? I don't want to mess up the picture, right? But OP is 2.5. This is 2.5. So I will write up here like this. I guess I'll write it on the inside. This distance, I'm going to do this. It's hard to do without messing it up. Hang on. I'm going to have to, hang on a second, guys. this distance here that distance right there okay is 2.5. Okay. So can we now find, so let me ask this question. Knowing what we know, can we find this distance now? Sorry, can we find the distance from Q2 all the way to P? Remember, that was one of the answers. That was the big aha moment. Yes, we can, because we know that this is equal to this. So this is 1.5, right? This was 1.5. So one of our solutions, the positive solution, is the distance from Q2 to P. So let's write down here. Let me write it where we can keep the, I want to see the circle, right? So the positive solution is the distance from Q2 all the way to P. It's that distance right there, okay? Well, we know what that is because that's just, so Q2 to P, that distance is equal to 1.5 plus 2.5. Somebody's mind's about to be blown here. What's 1.5 plus 2.5? Well, we can do it in pieces, right? 0.5 plus 0.5 is 1. 1 plus 2 is 3. So 3 plus 1 is 4. So this distance is 4. Now, have you seen the 4 show up anywhere? All right. So you found one of the solutions. All right. So now let's come to the big exciting part. Now, in order to find the other root, we simply need to find the distance from Q1 to P. All right, so I just want to make a point here. This is what I'm talking about. Like, this distance right here is the other solution. So this whole distance, Q2 to P, was one of the answers. That's 4. The other answer is the distance from here to here. Okay? So how would you figure it out? How would you figure this distance out? Let me really make that distance stand out for a second. Because you don't need any special math to do this. How do you figure this out? Well, look, you already know the radius. You know this whole distance is 2.5, and you know this is 1.5. So this is just 2.5 minus 1.5. What's that? 1? So this distance here from Q1 to P, so I should say this is the first positive solution. Right? The distance from Q1 to P is just 1. This is just 1. Because this is 1.5 and the whole distance is 2.5. So that's got to be 1, right? Wow. That's an answer? Well, it's negative. It's a negative 1. Okay, because this is the negative answer. So this is the second solution. Because we know there's two solutions, right? There's the first solution and the second solution. All right, so now that you know this distance, Q1 to P, so let me show you. So this is Q1 to P. It's a 1, not a comma. This distance is just equal to OP minus OQ1. Which is just the radius, you know? So, OP is 2.5. We found that out using the Pythagorean Theorem. It's 2.5. And O to Q1 is the radius of the circle, which is 1.5. (2.5) minus 1.5 is 1. Okay. So now, just so write that down. Okay, now, so this is the negative solution. The negative solution is the negative of the distance Q1 to P. Okay? Right, so we find that distance and then we put a negative sign in front of it. Okay. Focus. No, I'm not talking to you. I'm talking to the camera. Focus. Right. So we found Q1P. So Q1P is 1. So we say, well, if Q1P, if the distance from Q1 to P is 1, then the second solution, which is going to be negative, is just negative 1. Now, this is just amazing. Like, we've used geometry, we've used distances. So this is crucial. This is absolutely brilliant. So, so that means that just from the circle, using stuff you already knew, this whole distance here is the positive solution to the quadratic equation, and this distance here, if you put a negative sign in front of it, is the negative solution. So what does this look like on a graph? All right. Well, if you were to rewrite like your equation, you've got x squared equals 3x plus 4. If you forget all about what we just did and you just want to make this look like a regular quadratic, okay, what you would do is you would subtract 3x plus 4 from both sides. Right? You'd subtract the whole thing. And so you'd do minus 3x and minus 4, right, from both sides. And what you get is, you get this equation. You get x squared minus 3x minus 4. Okay? You can even write it as a function. So that equals 0. So as a function, that would be written f of x equals x squared minus 3x minus 4. Now this looks way more familiar, right? And so what have we actually learned? We've learned that the graph of this, okay, if we were going to draw a graph, okay, for drawing a graph of this, we've got one solution here at -1, so it crosses the x-axis there, right? This is the y-axis and this is the x-axis. And then the other solution is about how far did I draw that? About like that. So I'll be accurate this time, relatively so anyway. 1, 2, 3, 4. The other solution is right here at 4. if you look at the equation, the number that is not written here is a 1. Okay. The general form of the quadratic is ax squared plus bx plus c equals 0. So if a is positive, right, and it is, it's 1, that means that the graph is upward sloping, like a U shape. Okay, so now we haven't talked about vertex yet, but you can kind of sketch in this graph here. By the way, you also know what the y-intercept is, because this is what we call standard form. I should write this here. This is the standard form. Okay, and in standard form, C is the y-intercept. And that's just amazing, right? So C is y-intercept. So in this case, that's why I always tell students, identify A, B, and C, like right away. Make sure you do that. So A equals, B equals, C equals. Okay, so A equals 1. So we know the graph is upward sloping. And B equals -3. Okay, right now that doesn't mean anything. We don't care about B. And C equals -4, and that's the y-intercept. So the y-intercept, maybe I can draw a -1, -2, -3, -4. It's right there. Okay. So my my drawing is too close to the bottom of the page. The quadratic is going to go like that. Okay. So we can kind of sketch in the quadratic. It's going to look something like this. And then I'm going to cheat. Okay. So I'm just going to say it goes off the page, right, and it comes back up. We don't really care about the vertex just yet. We're not there. Vertex is the bottom of the graph. Yeah. But there's your quadratic, right? Isn't that amazing? I mean, am I alone here? Like, maybe I'm alone. I don't know. Maybe I've been studying, like, just doing too much of this, where I'm fascinated that there's a way to do this without, like looking at a circle. So the thing to do now is to take equations in this form that looks scary, x squared minus 3x minus 4, and realize that these are little paper tigers that you can just add 3x and 4 to both sides and make it x squared, get x squared all by itself. That was the key, right? That was Descartes' big idea. He realized that if I get x squared by itself on the left, then if the things on the right meet certain criteria, namely that the big criteria is that this number has to be a perfect square, okay? Then I can use this circle thing, right? And everything will work. So there are some limitations to what we've just learned, and those limitations are that what if S is negative? there's a little bit of a different method of solving it. So we're assuming here that when we get the equation, the original equation, we get, in standard form, x squared minus 3x minus 4, right? So when we add the 4 to both sides, we end up with a positive over here. So this is for certain circumstances where the s is positive. So this whole tutorial has been about when you have an equation in standard form where c is negative, its counterpart up in Descartes land is that c becomes s, right? That becomes positive c, right? So c is negative 4, then s is 4. Yeah. Okay, so there's your quadratic solutions as the geometry of a circle. Guys, that's unbelievable. So this whole distance is 4. I'm going to put that in there. That whole distance right there is 4. This distance is 1. So it's these numbers that turned out to be so crucial. So that was a solution, and then the negative of that was a solution to the quadratic. So that wraps up the Descartes method of solving quadratic equations using geometry. That is absolutely brilliant stuff. I hope you found some of that useful. I love doing this kind of math. The channel began with circles, and the channel has returned to circles. So I'm very thrilled. The Descartes method, where s is positive, how to solve it, quadratic equation. All right, thanks so much for watching.